Good morning, everybody. Thank you for being here. My presentation will be a bit different from you have been seeing so far for two reasons. First of all, we apply computational design, so we are sort of clients of people like Sphyrine and TOP. But the other reason probably you never heard about what I'll tell you is that we work on ceramics, and we don't work on ceramics like toilets or plates. We work with advanced ceramics, and by advanced ceramics I mean something like this. This is a porous burner called. So it's a burner in which the flame is constrained within its porosity. And of course, to have this component running, you need a material that withstands very, very harsh environments. And by that, I mean temperatures around 1300 degrees C and oxidative environment. So these are highly engineered materials, both on materials themselves and on their topology. Before going, I will outline a bit my talk. I will present a little bit my university. I'm coming from southern Switzerland, so I am in the Italian-speaking part of Switzerland, and we are within a University of Applied Science, and I will tell you a little bit about that. Then I will speak about from where I started, because this is very interesting also, and then why we choose computational design to go ahead, and then finally I show you some applications. First of all, we are in the very south of Switzerland, close to the Italian border, a few kilometers, and we are in Lugano. It's a town in the south of Switzerland, and we have a new campus right now just in downtown Lugano. Within SUPSI there is the MEMT Institute, the Institute of Mechanics and Materials, and I am heading the Hybrid Materials Laboratory. So before saying where you can go with the topology optimization in ceramics, I would like to tell you a little bit from where we started in talking about topology optimization in ceramics. For many, many years, I would say 20, 25 years, I was dealing with porous ceramics. And normally, before additive manufacturing, you were using porous ceramics by templating polyurethane foams. That's why we call them still foams, not lattices or whatever. And we were using a very, very old process, which is called the Schwarzwälder method, which is back to 1967. And it's a very simple method. It's you take a polyurethane foam, you cover it with a slurry, which is a mixture of powders and water or other solvents and binders. Then you heat treat this body, so you burn out all the organic part, so the polyurethane foam inside and all the organic binders. And in the case of most of the ceramics I'm working with, finally we do what is called silicon infiltration. So this body, which is comprised pretty much of carbon, we put this into a vacuum furnace at very, very high temperatures. We melt silicon, and silicon by capillarity is sucked in within the microstructure of this porous body. So it's very interesting to see from where we started. I mean, we were trying to understand how this really random structure, by random I mean really random, because it's a foaming process you cannot control at the end. We were trying to understand which were the weakest point of these structures and so forth. And so we started doing computer tomography of the foams we were making some let's say, loading, could be thermal, could be mechanical, could be whatever, And we were watching where is this material able to fail first. And talking about meshing, this was a real mess for us. I'm talking about something, this is more than 15 years ago. So making the mesh you see here on the left, it was a completely a nightmare because we were starting from a computed tomography, meshing it, fitting all these hell of a triangles together and trying to make something that was working for a simulation. So it was a real mess. And the best way to work with bigger structure was this way, was producing cells, easy to model with a CAD model like NX, replicate those cells which were pretty much working as a foam, as a stochastic foam, and then saying that pretty much we were doing what a foam, we were, let's say, simulating what a foam should do. In this case, this is a European project for a sandwich structure for re-entry vehicles, and we were simulating how this structure bumps up when it's heated up on one side and it's cold on the other. And then it was 2005, 2004, I saw for the first time a Tour Eiffel printed by fused filament deposition. And for me, this was mind-blowing. I mean, because I immediately saw a foam. For me, this was a foam. So I started having a cartoon in my head, taking this foam and process it as I was usually processing it. So all of a sudden, what I was developing to understand what was going on became the starting point for making what I want. So, I mean, it's a completely reverse way of engineering materials. And besides all the cells, all the wonderful topologies that you saw so far, I mean, you cannot believe how just doing a simple thing, like having a bunch of cubes, cubic cells into the space, okay? And flowing a gas, liquid or whatever, into this cube. If the face of this cube are perpendicular to the flow, you will get a flow like this, okay? So it's a straight flow. Now, the same cubic cell, I just tilt this cell of 45 degrees in the 3 direction, and just the same cell, the flow will behave like this. And this is amazing. I mean, you just change everything. This is a mixer on the bottom, and in the other case, it's a completely different flow. So, I mean, this is really changing the game for us, especially for the burners. So we, for many years, we started playing with these lattices. At the time, we didn't even know that it was called computational design. We were just CAD drawing things and testing them. And of course, we started with MATLAB. We were assigning different thickness to whatever. Then grasshopper, rhinoceros came out, so we were able to grade the pore size in each direction, and blending cellular structures to have different flows within just one pipe, for instance, which is this case. And together with my colleagues, we were making a lot of simulation, thermofluidodynamic, thermo-mechanical, whatever. And so this is really, from, let's say, 2010, this really flipped over the way we were doing these things. Now, a few words on what actually we do with those numerical models. We have different ways to print these numerical models. On top left, you see a so-called binder jetting machine. It's a machine that deposits a bed of powders with a given thickness, and just printing an ink you will create layer by layer a 3D structure. On the right, top right, you see a stereolithographic machine, very precise, but with the optical limitation. And also on the bottom left, you see a powder bed fusion machine for a process in which we were preparing a porous body for a further infiltration. Okay, and finally, and this is the part more of my experience, we have a bunch of ways to thermally treat these materials and convert them from a, say, polymer ceramic composite to a fully ceramic material. Okay. So finally, let me give you some examples of many years of experience. We have been working a lot in renewable energy, in aerospace, in industrial heat management, and also in filtration. Let's start with this. Imagine that you have a tube which is heated from outside, and you want to heat the fluid which is flowing through. If you don't put anything, it's very ineffective. You just heat the first layer of the fluid touching the walls, the inner walls of your tube. As soon as you put a porous body, you start increasing the mixing of the fluid on one side. You have more surface to have a heat exchange, and you have also guides for the heat to be transferred from the outside to the inside by conduction. But that's very limiting, because if you put a regular structure like the one on the left here, you don't fully exploit all the ways that heat is transferred, because heat is transferred by conduction, convection, and radiation. In a cell like this, radiation, it's somehow shaded, okay? And then if you think of a tree being inspired by nature all the time, you see that the tree has most of the leaves outside, and the lower you go, the less are frequent the leaves, okay? So there is a kind of graded, let's call it cell size of this porous body, which is the tree. And so if you reverse this idea, and this is, let's say, the idea of this cell, in which we were grading with MATLAB the cell size. So here there was a big cell, and radially going outside, the cells were getting smaller and smaller. In this other case, the smaller cell was inside here, and the bigger ones were here. And so this proved to be, I'm sorry, I'm using, in this one, the smaller, and this one is the bigger. And so if you want to let the radiation penetrate from outside to inside, of course, this solution is the better, because the outer cells are not shadowing the inner cells. So you get a much more efficient heating of your tube, you see here from the temperature distribution. So that's one case. Another case was putting together mechanical properties and thermal properties. This was a process with DLR. DLR, it's the German NASA, let's say. We were developing a re-entry wing for a re-entry vehicle, and this is this wing tested into a plasma wind tunnel, so very high flows, a lot of heating by friction. And we were making a sandwich structure, like you see here, in which the inside was filled with the ceramic material, and this. The goal of using this was twofold. On one side, you have a sandwich structure which keeps integrity. On the other side, we were flowing a gas inside here, and we were removing heat from the leading edge, which you see here is the most heated part of it. You see here the setup before testing. You see here the sandwich structure here. This is a CMC. It's a ceramic matrix composite, able to withstand high temperatures. You see our structure inside here, and you see the sample after the test. It survived something like 20 tests, 20 re-entry tests, and you see some oxidation here, of course. Another application is a heat exchanger for using a temperature to recover heat from a concentrated solar panel. In this case, we were using a porous body inside here. This is a plate and something like a plate and fin heat exchanger, very compact, and it was used in a project it's called hydrosol to produce solar fuels. This is another application in which we were developing a porous body here to enhance heat transfer from, let's say, a gas to a phase change material for heat storage. This was conducted with EPFL in Switzerland, and was part of a huge project, huge Swiss project to recover, let's say, industrial heat. Another very interesting project was developed with, again, in Switzerland and within a European project. It's called the thermo-mechanical heat storage. It's kind of complicated. By sorbing and desorbing water from a solution of water and sodium hydroxide, you can store it in the summer, having a highly concentrated solution of water and sodium hydroxide, and release heat in the winter by adding more water again and producing heat by this way. To do this, you needed a lot of surface to have this exchange. And so we were developing these weird structures, periodic structures, in which the goal was to, during the dripping of this solution, allowed more and more wetting of a surface. So you see, for instance, we start here with 1 drop, and we'd come out on the other side with 3 drops, meaning that the flow was spreading. Finally, an application on, this is the most, let's say, advanced application we are doing so far, is called, in catalysis, you normally heat a catalyzer by heating it from the outside, but if in this case, if you put a porous body within your reactor and you heat it up by Joule effect, you can, by depositing the catalyzer on this porous body, you can, say, have a very efficient way to heat up your catalyzer. And so with the topology optimization, we designed these structures, which are, let's say, heaters made of silicon carbide with a topology optimized both for flowing and for heating up by Joule effect. This thing was mounted within a reactor. This is a mock-up of the reactor. You see it inside. You see the current is flowing from here to here, through here, of course. And in this case, the reactor was a reactor in which we were cracking methane. So we were feeding this reactor with methane, and we were getting as 2 products, carbon, which is very much used for batteries, and hydrogen, which in our case was a byproduct, very interesting byproduct, by the way. So you see here that we are producing carbon in this way. And this is a very interesting way to produce carbon, because normally carbon is used to be produced with the methods which involves a lot of production of a lot of CO2. So this is very, very interesting. Finally, where to go? Well, yesterday Bradley was, I totally agree with him. The next step for me is to go backwards from where we are heading now. I mean, we start from a field and we get the structure which better fits with a fielded, whatever it is, thermal temperature distribution, loads, whatever, stresses. And so this is definitely the way to pursue, to further increase the efficiency of these kind of structures. Yeah, this is my team, which I would like to thank very much. And finally, if you are interested in ceramic structures and ceramic structures produced by additive manufacturing, we just finished to write a chapter of a book of handbook of additive manufacturing. So can find more details of what I was saying to you so far. Thank you very much.